Hi guys, I have received an FRNISI GM328A component tester, and I thought we would do a quick evaluation since I have already evaluated the other component testers that I have, but this particular one here, they've added some features to it, like a square wave signal generator, a frequency meter, PWM, output, capacitance, transistor, voltage, whatever. So we're going to have a quick look at this thing to see what it does compared to some of the others that I have. Now, I believe that most of these Chinese component testers are actually based on some circuitry and some work done initially by some German guys, and the project is open source, so there is quite a lot of documentation on it. And here is the document here. Karl-Heinz Kubler wrote this document. I think there was two guys involved with it, and eventually, in any case, they released this thing as open source, and the Chinese have taken it on, and they started producing these component testers on that on the work and the circuitry that these guys did, and there is a lot of information on it, circuit diagrams, and how the thing works and all that kind of stuff. So I believe that most of these things are actually based originally on that work, but by now the Chinese have actually evolved it and added bells and whistles to it and some updates and what have you. On the left over here is the actual documentation that you can download from the FRNISI website, but it's only like 2 pages. There isn't much there, and it's a doc file, and it's kind of badly translated, but it's readable. So I thought we would go and have a look. So what I have is, this is the device here, and as it's very similar in behavior and what it outputs to this device, so that makes me think that this one is probably a slightly earlier version of this. I also have this device here, which may well have some relationship to it, but I'm not sure. It is kind of different, and this one we won't be comparing it against because it is not very accurate, and we will just compare it to these two. And this is my fancy expensive component tester, which has a USB output, so we can see it on the screen. And so we're going to compare these guys together. And here is my little toy pocket oscilloscope that actually is able to output. It's a function generator as well as a little oscilloscope. Right now it's generating a 1 kilohertz signal, which we're going to feed into this thing and see what the frequency counter thing is like. This thing is actually quite accurate. I've tested it on my big frequency counters and what have you. So if this says it is outputting 1 kilohertz, it should be very close. But in any case, we'll test do the component testing first. So let me zoom in a little bit here and see what we can see. Okay, so let's have a look. I got a few resistors, I should say, here. According to the multimeter, which you'll see at the top there, this resistor is 9.940 kilo ohms. Now the way this works is I marked it with some felt tip pins. This is red and that's black. So this is like pin 1, all 6 of these. And these are pin 3, all 6 of those. 3 at the top, 3 at the bottom. And only the middle 2 holes are pin 2. So when you put transistors in there, you will have to put the middle pin in one of those middle pin there. I don't know exactly why they laid it out like that. It works. On these guys here, as you can see, they got pin 1, 2, 3, 1, 2, 3, 2, and so on. I've forgotten what the KAA is all about. Something about cathode and anodes or something on diodes, I'm not sure. Alright. Nine 9,901 ohms. 9,893, 95, 96. Can't make up his mind. 9,884. I just push the button again off screen, and now it is 9,939 to 42. I've already forgotten what did the multimeter say. Well, I guess that's not too bad. 48 and set 42 or something like that. Now, what does this little guy here say? $9,949, and it actually holds steady. I guess they are close enough to be within range. Okay, let me see now. This is a 220 ohm resistor. .3 kiloohms. I thought it was a 220. It's always hard to read those blue resistors. Okay, anyway, 100.3. One 100.22. 100.9. All these things are slightly different. But the multimeter here, the bench multimeter says it's 100.19.2. So I guess this guy is actually a little more accurate if the multimeter is accurate. Okay, so I put a 330 ohm resistor in the multimeter, You can see at the top right there, and it's coming up 329, 328, 329, 04, 05. So this is a lower value resistor, and it seems that there's more variation in the lower value ones than in the higher value ones. 327.4. $327.3. As I said, these two guys seem to come up with very similar values. Of course, 328.9 on the multimeter. Of course, I wouldn't actually use these things for measuring resistors. I'm just doing this to see what's happening there. Okay, now let's have a look at some LEDs. This guy here doesn't do resistance, so therefore I didn't include those together. So first, this is an LED, a green one, but connected there. So let's switch to the we can get rid of the multimeter because I don't I'll be using that now. Okay. Okay, so the DCA Pro is coming up with it's an LED, forward voltage 2.56 volts, and some guff about it over here. 2.56 volts, and it recognizes that it's an LED. I don't believe that any of these guys understand anything about LEDs. I just tell you it's a diode. But let's have a look. Two and a half volts. It does give you some other information which the other one doesn't. Reverse voltage, reverse current 2 nanoamps, capacitance 50 picofarads, but it claims to be a 2.5 volts diode. It doesn't tell you it's an LED. I guess not that that matters too much. It pretty much agrees, except it has less capacitance on this one, 2.51 volts. Now they use different current on those other ones. On this DCA Pro one, it uses 5 milliamps, so therefore 2.56. So a slight variation in voltage there might be due to a different currents that they're using. Okay, so that was the green one. Let's try this blue one over here. Okay, then it recognizes an LED. Now it is 2.712 volts at 5 milliamps. .69 volts on this one. .68 volts on that one. Anyway, that's how they work. Now here is something interesting. This is a NEC C1093 it is marked as, and it looks like a transistor, but apparently this is a voltage reference, a bit like a TL412, I think. And when you plug it into this DCA Pro, it actually refuses to look at it. Oh, well, it actually tells me it's a diode. Last time I plugged it in. Oh, wait, that's why. I've got this. I don't have the third leg connected. Sorry about that. So it thinks is an NPN digital level transistor with some crazy HFE at 4070, and that is not actually what it is. They all have their limitations, these things. See, it thinks it is an NPN transistor with a HFE of 2. So, and the other one, this one over here, actually comes up with very similar information. But what it actually is a little voltage reference. It's closely akin to a Zener diode. So that's interesting. None of them can deal with that very well. Here we have a diode. A little diode. And it just says diode junction, but it has a forward voltage of 0.226 volts, which kind of tells us that it's a Schottky diode. .241 volts, 241 millivolts. It's 20 millivolts higher, and it actually claims to have a reverse current of 1.5 microamps, which means it's kind of, if that's true, it might actually be a germanium diode, but I don't know. Okay, I just looked it up. It is actually a Schottky diode, even though it says it has a little bit of reverse current. It's a 1N5819 marked as. $240 millivolts, and it also is reporting a little bit of reverse current, which is actually correct, isn't it? Because Schottky diodes do have that facility. Okay, now here I've got a little LED flasher unit thing. It actually has some circuitry on there. Not much by the looks of it, just a 0 ohm resistor and 2 LEDs. So it is actually probably 2 LEDs in series. So if I test it here, it is coming back with it being a diode. It doesn't recognize it as an LED, but it's got 5.12 volts. Here, the two LEDs are in series, that's why it's 5.12 volts, 2 point something or other volts each. But when you plug it into these guys, something interesting happens. It's testing it, obviously. See, it's flashing. Now, one of the features of this thing is why it keeps flashing is that if you plug something in between the red and the black there from pin test point 1, test point 3, it actually stays on. And the idea is that you can just add. You don't have to keep pushing the button. You can just put new components in there, and it'll keep testing it. That's why it keeps going. But it thinks it's a capacitor of 419 picofarad. It doesn't recognize it as an LED at all, or even as a diode. And I believe this thing does the same thing, which again makes me think that it is based on the same circuitry. It doesn't keep testing it, of course, like the other one does, but 415 picofarad capacitor, so it's wrong. So the Atlas Pro does DCA Pro does recognize that it's a diode of some description, but these guys, they don't know what it is. Now here is an ordinary little diode. Got to hold the button down now to get it out of that. Okay, it recognizes it that it's an ordinary silicon diode, obviously 699 millivolts, 2 nanoamps reverse current. (702 millivolts), a little bit more than the other one reported. Have a look what we get. The DCA Pro. Diode junction 0.683 volts. Yep, ordinary diode. Alright. Now these guys here can also do capacitance. This is 100 nanofarad capacitor. Alright, let's try that again. (98.88 nanofarads). And that ESI value, of course, is meaningless on a little 100 nanofarad capacitor. And because we don't know, it doesn't tell us what the frequency is, and if you make the frequency go up, the ESI goes down, so it's not useful information on a little capacitor like that. $98.18. Now, if I connect this up to my LCR meter here, which is accurate, I get that I'm running that at 10 kilohertz. And that's what I mean if you don't know. So we got 98.4 nanofarads, and the ESR at 10 kilohertz is 4 ohms, which makes me think that it is running at maybe 12 kilohertz or something. This tester, because it says 3. In any case, that's accurate enough. Here I have a little unknown transistor. This is kind of interesting. Let me untangle these leaves over here. I'm going to hook this into the DCA Pro. This is an old transistor, I presume, that maybe even 40 years ago that I might have bought in a little bag or something with unknown components or whatever. It is not, that has no markings on it whatsoever. And if I plug it into the DCA Pro, which has no components detected, possible the diesel cannot detect any of the supported component types on the probes. So I don't know what is different about it, but when I plug it into our tester here, see where the mouse is. According to this thing, it is an PNP with a HFE of 660, and they're testing it at 6 milliamps, and it has a voltage space to emitter 723 millivolts, which could be true for a what do you call it, a silicon transistor. And indeed, if I plug it into the other one, it tells me something similar. These same kind of information, 6 milliamps, 660. This is what makes me think it is based on the same circuitry that was done by these German guys. So I don't know, this is kind of interesting. My fancy, expensive DCA Pro can't actually analyze what this is. But when I put another transistor in here, well, let's do this one first since we got that set up. This is also an old transistor that I've had for ages. This is an NPN, HFE 427, at 4 milliamps, voltage base to emitter 668 millivolts, and it seems to have a little bit of reverse leakage current at 4 microamps, and so on. And I think you'll find out that they will all agree on that. Looks like this one is slightly faster than the one there. 429, 678 millivolts, 4 milliamps. NPN. NPN. Pretty much similar information there. So that one works. Now here we have, I think this is a germanium transistor. I don't know if anyone still uses germanium transistors. Yeah, but wait. Yeah, PNP. So this is voltage-based emitter 202 millivolts. That is different. It says 2.77 at the Atlas Pro, and but they're running it at 6.8 milliamps, and the DCA Pro used 5.02 milliamps. So maybe that's why there's a difference. But the DCA Pro tells you that it is a germanium transistor, and this one doesn't. You have to look at the voltage, and I think I have it in the wrong socket there. Yeah, that will be better. BNP, EBE 2.04 millivolts, 6.8 milliamps. Anyway, that's how germanium transistors come up, and I think we've pretty much done sort of component testing here. So let's put this thing to sleep, and we can put this thing away. And now we're going to test some of the other features that it has. Okay, so according to this information over here, that the input at the top here is going to be for frequency measurement. So let's have a look. So I've got to start with a 1 kilohertz, 2.55 volts peak to peak signal square wave coming out of this thing here. So let's hook it up. Okay, so we are in the little menu here, and we select frequency 1000 hertz. That's correct. So let's have a look now. 2 kilohertz. Yep, 2 kilohertz. Hundred and 20 kilohertz. Yeah, so far so good. 2000 kilohertz, that's 2 megahertz. Can't remember what the, obviously this thing can only, looks like 2 megahertz is the highest as it goes anyway. How do you change the, oh, there you go. This is a triangle wave. Let's go back to 123 point 1.3.45 kilohertz. That's pretty accurate. And it seems like it doesn't mind having a triangle wave, square wave, sine wave. This is random noise. This is going to not work very well. This is a different waveform, like it has little peaks and valleys in it. But yeah, it's good. It seems to that part of it seems to work. So now let's have a look. There is some sort of voltage measurement over here. I have no clue as to what limitations it has, but I suspect that it is probably more useful for little batteries and things. Okay, so I got it connected to my bank's power supply, which is set to 1.23 volts, and that's working. I don't want to go too high in voltage on this. I do not know what its limit is. 5.23 volts. Now it deviates a little bit. 6.23, 7.23. Let's go to 12.5. That's relatively accurate. I haven't looked at the specs. I don't know what the maximum voltage is that this thing can handle, so it works. Now let's have a look at the function frequency, the signal generator. Okay, so 100 hertz, and indeed that is what we get here. Looks like 5 volts peak to peak as the output. (250 hertz), 439 hertz, yeah, 1 kilohertz. Five thousand hertz, 10 kilohertz, 25 kilohertz, 50 kilohertz, 153.8462, wherever that comes from. 250 kilohertz seems to be fairly accurate. Now it's starting to look a little less like a square wave. One megahertz. (1000 megahertz). I don't know what that's all about. 1000 megahertz is not something that this little oscilloscope can deal with, if that's really what it is, because that's 1 gigahertz. Anyway, that seems to work. But let's have a look now. There is something about a pulse width modulation. For some reason we got a 7.8 kilohertz signal, but we can indeed see we can indeed adjust the width. Okay, well, it works for whatever it is good for. Another thing, there's a bunch of stuff there that I haven't looked into and I have no clue what they are for. If somebody knows, you can put it in the comments. DS18B20. There's an IR decoder and an IR encoder, but it would be unclear to me where you would put the sensors or something. And DHT11. Different modes. C plus ESR at TP1 :3, whatever that means. Okay, so I think that's all I can do because I am not sure unless I do some more research into what some of the other settings are for. Probably experiment with it. But it seems to work. It's relatively accurate, I think. And it also has, of course, a section here for SMD components that you can kind of place on there. And I don't know, I think I might make a little box for it on my 3D printer. And if I do, I'll make that into a little project so you can see how I do that. But not, I've got some other things to do first. I don't know when I'll get to that. Anyway, that's it. The FRNISI GM328A component tester. Until next time.